Our first objective in this lesson is to be able to find the area of a region that is between two curves, and we want to do that using integration. So for example, say we have a curve of a function f and another function g. What we want to do is we want to find the area that is between f and g and a and b. So this area in here. And how we do that is we already know how to find the area that is just under f between a and b. So this entire area here. We know that we find that area by integrating f from a to b. We compute the integral of f from a to b. Similarly, we also know how to find the area that's under g and between a and b, and we find that by integrating g from a to b. So if we know how to find the red area, and we know how to find the blue area, then to find the area in purple that is between a and b, we integrate between a and b and between the graphs of f and g. We integrate from a to b of the larger function that was on top, f of x, and from that we subtract the smaller function that was on the bottom, so we're subtracting the blue area that's not in between them, and we integrate that with respect to x, and that gives us the area between those graphs, between the vertical lines x equal to a and x equal to b. So here we have our first example where we want to find the area of the region bounded between a parabola and a line between two given x values. So the first thing I'm going to do is I'm going to get started and I'm going to do a very rough sketch of what this region looks like. So I'm going to start by sketching the parabola. Y is equal to x squared plus 2. That is a parabola that opens upward with its vertex at the point 0, 2. Next, I'm going to sketch the line y is equal to negative x. That is a line that goes through the origin and has a slope of negative 1. So that line looks like that there. So we're interested in finding the area between these two graphs, between x is equal to 0 and x is equal to 1. X equal to 0 is the y-axis, and x equal to 1, I'll say, is about right there. So the area that we're looking for is this area here in this red region. And to find that area, we compute the integral from the lower limit of 0 to 1. I'm getting that from the bounds on this region, the vertical line x equal to 0 and the vertical line x is equal to 1. Then on the inside of the integral, we are going to do the top function, which in this case is the parabola. The top function here, that is the x squared plus 2. And from that, we are going to subtract the bottom function, which is the linear function, that is negative x. So I'm subtracting a negative x from that, and we are going to integrate this with respect to x. I'll first just clean up the inside of the integral. We have x squared plus 2 plus x that we're integrating. We'll integrate each three of these terms using the power rule, increasing our exponents by 1 and dividing by our new exponents. And then we will apply the fundamental theorem of calculus to evaluate this integral from 0 to 1, leaving us with 1/3 plus 2 plus 1/2, giving us our final answer of 17/6 for the area of this region. In our second example, we again have two functions that we want to find the area of the region enclosed by them. Notice that in this example, we are not given two vertical lines. Back here, we were given two vertical lines of x equal to 0 and x equal to 1. These two lines there. We're not given those lines here, so let's first take a look at what this region looks like so we can start to figure out what the limits on our integral will be. So I'll start by sketching the parabola. Y is equal to 2 minus x squared. That's a parabola that opens downward and has a vertex at the point 0, 2. It looks like this. Then we also have the line y is equal to x. That is a line that goes through the origin with a slope of 1. So that line looks like this. So we can see that eventually the line and the parabola do touch each other at some points right here. We can also see that the parabola is on top and that the line is on the bottom in the region that is bounded by these two. What we need to know is we need to know what are these x values here where those two regions meet. So to find those x values, I'm going to set these two functions equal to each other. I'm going to set the parabola of 2 minus x squared equal to the line of x, and I'm going to solve this equation to see where these functions are equal to each other. This is a quadratic equation, so I'll first just get 0 on one side, and now I'm going to work on factoring this expression. Looking for two numbers that multiply to -2 and add up to a +1. That's a +2 and a -1, giving me solutions that x is equal to -2 or x is equal to +1. So I now know that this x value here is -2 and this x value here is +1. So sometimes we're not given x values from which we want the area to be in between. Sometimes we have to realize that the two graphs intersect each other, and it's our job to algebraically find where those intersect. Now that we know where those two functions intersect, we can use that information to set up the integral for our area. Because now we know the area will be the integral from the lower limit of -2 to the upper limit of 1. And on the inside of the integral, we need to make sure we're doing the top function, which is the parabola 2 minus x squared, minus the bottom function, which is the line of x. And we will integrate this with respect to x. So I'll integrate this using the power rule, giving us 2x minus x cubed divided by 3 minus x squared divided by 2. I increased all of my exponents by 1 and divided by my new exponents. And now I'm ready to evaluate this from -1 to 2. I'll apply the fundamental theorem of calculus and first plug in my upper limit of 1 and then subtract and plug in my lower limit of -2. And we'll simplify and evaluate this to give us a final answer of 9/2 for the area between those two curves. In example 3, we're given that the graphs of sine and cosine intersect each other infinitely many times, and we want to find the area of one of the regions formed by those points of intersection. So let's start with a graph of the sine and cosine function so that we can determine which function is on top, because that is important when we set up the subtraction in our integration, and also to help us visualize where these points of intersection are. So I'm going to begin by graphing the sine function, which crosses through the origin, and then increases, and then decreases, and then increases again, so on and so forth. And for instance, I know that the sine function has its peak when x is pi/2. And I know that it has its lowest point when x is at 3π/2. And I know it's 0 at pi. Now I'm going to come in and sketch the cosine function, which does not go through the origin. It goes through the point 0, 1, then decreases when x is pi/2, has its minimum value of -1 when x is pi, and then increases and is 0 when x is 3π/2. Like so. So this graph gives us a rough sketch of one of the regions that are formed when sine and cosine intersect each other. Now, note that the functions do continue on in this pattern forever, and they form infinitely many regions like this. For example, if I were to continue sketching out the graph of this cosine function, I would see something like that. And although this is a rough sketch, you can kind of visualize that that area shaded in green is the same thing as this area shaded in purple, even though this is a very rough sketch and it's not exactly right. So finding the area shaded in green is going to answer our question, because we're only asked to find the area of one of those regions. In order to find that area, we need to know what are these points of intersection, where those graphs meet. And so to do that, I am going to set the functions equal to each other. I'm going to set sine x equal to cosine x, and I want to solve. This goes back to 172, solving a trigonometric equation. You can think of where the y-coordinate is equal to the x-coordinate on the unit circle. Alternatively, you could divide both sides of this equation by cosine x to get sine x divided by cosine x is equal to 1, which is the equivalent equation to tangent x is equal to 1. And we know that tangent is equal to 1 when x is equal to pi over 4 in the first quadrant or 5 pi over 4 in the third quadrant. So those are the 2 points of intersection that we're seeing on our graph. So we can now use those to find the area, because we know we need to integrate from pi over 4 to 5 pi over 4 of the function on top, which is the sine function, minus the function on the bottom, which is the cosine function, and we're integrating with respect to x. The integral of sine is negative cosine x, and the integral of cosine is sine. So we are now evaluating this from pi over 4 to 5 pi over 4 using the fundamental theorem of calculus. So we have negative cosine of 5 pi over 4 minus sine of 5 pi over 4 when we plug in our upper limit, and from that we are subtracting negative cosine of pi over 4 minus sine of pi over 4 when we plug in our lower limit. So now we are ready to evaluate this. Cosine of 5 pi over 4 is negative root 2 over 2. It's the same value for sine 5 pi over 4, so we are subtracting a negative root 2 over 2, minus cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is also root 2 over 2. So we have positive root 2 over 2 plus root 2 over 2. I'm distributing this negative. We are adding another root 2 over 2, and we are adding another root 2 over 2, which leaves us with 2 root 2 as our final answer.